So welcome to the Exceed MPI workshop. I'm John Urbanek, coming to you from Pittsburgh Supercomputing Center. This is the workshop that most excites me as a parallel programmer, because this is the most powerful of all the parallel programming techniques. And now we can go into what I think is a really interesting talk about how all of these, how MPI relates to the other alternative programming approaches, because now you have enough knowledge of an actual approach, of the most important approach, MPI, to make valid comparisons to other things, and not just a bunch of hand waving and buzzwords. So now we can talk about these other ways you might do parallel programming, and we won't have to just talk in the abstract. We can talk about concrete examples, and we can compare things to a real practical approach, maybe the most practical approach, which is MPI. So this is the bookend for the intro to parallel computing, where we mostly talked about hardware and the kind of hardware we're going to have to use if we want to do successful parallel programming these days. And now instead, we're going to talk mostly about software here. And so let's talk about how well codes scale first, before we start trying to define metrics of success, how good or bad something is. Well, we need some quantitative way to talk about how successful we are with doing a parallel port. And fortunately for us, there is a very relevant metric that applies to almost any application that you parallelize, and that is how well does it scale? As we run on more hardware, does it run equivalently faster? And most applications follow some kind of curve like this, where as we add more and more hardware, they don't increase linearly. So a perfect or a well-written code, as you run on 100 processors, speeds up 100 times, on 1,000 processors, 1,000 times. But almost every code falls short at some point. And so the question is, how far do you get? For example, this code we're looking at right here, this blue line, it scales pretty well to about 1,000 processors. It's really speeding up still. It's not scaling perfectly. So on 1,000 processors, it might only be running 600 times or so faster. But that might be a big enough win for you. Certainly 600 times faster puts you in a completely different ballpark than people that don't have a parallel code. You can do a simulation in a day that would take them 2 years to do. But we can see with this code, there's really no point in running it on 2,000 processors. Say it doesn't speed up that much more, and yet you're hogging a lot more expensive hardware. So the scalability gives you a very good idea of how well you've succeeded in scaling your code up. So that's the metric you want to ask of anybody that's talking to you about parallel programming, either their application or the tools that they're using, their programming language or their hardware. They say, I built this cluster. You can say, well, how well do codes scale on your cluster? You built your departmental cluster with a dozen computers, and you're running this really important application, this computational chemistry package. If you run on all 12 nodes, does your code speed up 12 times versus one workstation? Or does it speed up 3 times because you've got maybe a bad crossbar, an inadequate hardware crossbar switch? So the scalability metric is a very good reality check. There are 2 ways, however, of basically scaling your code up, and they're both equally valid and relevant, although one of them is called weak scaling and one of them is called strong scaling. Don't let that bias you to think one's more meaningful than the other, or more important. Weak scaling is where we've got a problem, like our weather problem, for example. Say we're meteorologists. Let's say we're trying to predict all the weather, and we might want to get more accurate results, which means we need a finer grid. And to go to a finer grid, maybe a 10 times finer grid, we need a lot more processors, unless we're willing to wait a lot longer. Even if we have the memory, let's assume the memory is not an issue. If we go to a finer grid and we keep it as a serial problem, it's going to take that much longer to come to an answer. And for our weather forecast, having your next day forecast take a week to produce isn't really very useful, is it? So instead, we throw more processors at the problem and get a more accurate result, but we can also get it maybe in the same amount of time. On the other hand, so whenever you take a problem and you scale it up and you make a different, more challenging problem, that's weak scaling. On the other hand, sometimes you want to take the exact same problem and you want to get a faster answer. And that's called strong scaling. And that can be very, very relevant for something like tornado prediction. If we're doing tornado prediction, we might have a model that's very accurate, but it takes 3 hours to run. And we need real-time tornado prediction. We need that model to run in a couple of hours. So we parallelize it, or excuse me, a couple of minutes. So we parallelize it and it runs in a couple of minutes. So it's the same problem, and you measure how much faster you're running. So they're both valid use cases for different circumstances, but there are different types of scaling. So when somebody's showing you a scaling graph, they might say, as I'm running on more processors, I'm running a more challenging problem. I ran on 1,000 processors, but I ran 1,000 times more grid points, and that's how it scaled. Or they might say I ran on 1,000 processors and it ran 1,000 times faster, and that's how it scaled. So they're both valid, but make sure you're looking at the one that most interests you. Now, when you go to scale things up, there are impediments in your way. The most obvious one of which is something called Amdahl's law. And Amdahl's law is simply an algebra statement that tells you that your code is going to be bottlenecked, handicapped by the part of the code that is inherently serial, that you don't speed up. So let's say we take a code and we run it and we time it, and there's a bunch of different things that happen in the code, and we notice that parallelize it. We do a good job.
We lost you for about 5 seconds here, last sentence.
Oh, thank you. So if we take that code and we parallelize, yes, and there's my warning, always too late. If we take that code and we parallelize it on 5 nodes, then that 50-second section of our code is going to run in 10 seconds. And so our code now altogether takes 60 seconds to run. And that's pretty good speed up. And you might have 5 cores on your laptop. Now it runs twice as fast. So, hey, good for you. That might be useful. But if we take that code and we run it on 1,000 processors on some big cluster or some supercomputer, the section that we parallelize speeds up to very much. So it's only taking a fraction of a second. But the serial parts that we didn't speed up are still taking 25 seconds a piece. So it really only sped up by a factor of 2, even though we're running on 1,000 processors and much more expensive hardware. And that's probably not a very satisfactory result. We're not happy if somebody's running on bridges and they're using a lot of hardware and they're speeding up by a factor of 2. So Amdahl's law is basically just this in algebra form. If we just do the algebra of what section of your code is left behind and how much is to slow things down, we find out that we get some curves that look like this. If half of your code is serial, there's really no point on running on more than 4 or so processors. Things just don't speed up. As a matter of fact, in the real world, the overhead of stuff, this curve will even start to tail off and slow things down. And we can see that even if 1% of our code is inherently serial, there's really no point in running on more than maybe 1,000 or so processors. And so this is Amdahl's law. Now, Amdahl's law was for a long time, early in my career when parallel computing was still getting its feet under it, was a reason why people would tell me there's no point in them porting their code to parallel because there's going to be some serial part, it's not going to speed up. And most codes have some inherently serial stuff. Algorithms are just inherently serial. And so Amdahl's law is always going to get in the way of parallel computing. And there's no point even building these big clusters because Amdahl's law. And it was very much a battle. And I had to twist arms to get people to invest in doing a lot of parallel computing. Now, of course, people recognize that you can pick up any journal, any scientific paper, and find codes that are running on hundreds of thousands of cores, and virtually everything that's done in computational science anymore is run in parallel. So people are a little less inclined to just dismiss things up front because Amdahl's law. But nevertheless, it still is a relevant phenomenon to be aware of, that if you don't port your code to parallel, the serial parts of it are going to catch up with you at some scale. Now, the impressive thing about this modern state of parallel computing is that we have many, many, many codes that run well over 1,000 cores. And that tells you that it is entirely possible to write codes that really have no significant serial part at all. That used to be a really hard thing for me to convince people of. I'd say there's really no reason any of your code has to be serial. And they'd always say something about, well, IO or this. The bottom line is there are plenty of codes in many different domains across many different algorithms doing completely different types of science that scale well enough to tell you that not even a fraction of a percent is inherently serial. So don't let anybody discourage you from parallel computing with the old Amdahl's law argument, because like I said, these days, there's plenty of evidence, so I don't get in those arguments. But likewise, be aware that it is an issue. So if you only port part of the code and make it parallel, you're opening yourself to Amdahl's law. Okay, so we're going to write some scalable code. So what are you going to pick to do it with? And you now have a tool to work with, MPI. So like many people, you might grab the tool that's at hand. And in your case, you're lucky that you happen to have a very effective and good tool. But for a lot of people, they don't have anything, or they have something and they're going to use it, regardless of its fitness to the problem at hand. But you have lots of choices. I wrote this slide a long time ago with the list of choices at that point in time, and the list has only grown and it changes and morphs all the time. So I don't even update this slide because what's the point? Today I could go out and find easily several hundred different proposed and reported techniques for doing parallel programming, because somebody's always writing a new parallel programming language or a new technique or a new library or just a whole new paradigm way of thinking about things. So you have countless choices in parallel programming. There's an explosion in the 90s and it's only continued since and gained momentum. And it can be overwhelming. Now, as I said, if you have a tool at hand, there's a tendency to say it's going to be the tool I'm going to use. If all you have is a hammer, everything looks like a nail. Well, that's equally true, maybe more true in software than anywhere else. So, whatever language somebody knows, well, that's the best programming language for whatever they're going to do. Well, whatever parallel programming approach somebody knows, that's what they're going to use. And so you have to be careful because people have that bias. And when you get advice from people, they're going to have a tendency to be like, yeah, well, this is what I learned. And so it's good for everything. And because there's so many choices, the odds that they're giving you one that doesn't have staying power are reasonable. And by the way, the other thing to note about this list is that most of these ones on this list are now completely, totally defunct and gone and obsolete. And people that committed to using them are sad because they've got something that now maybe can't even compile, or it's got a ton of bugs that nobody's ever going to fix, outstanding bugs in the system. So you do not want to just pick something, with enthusiasm, like, okay, well, this is going to be around, because when it gets abandoned, when it doesn't gain critical mass, it doesn't have enthusiasm, it doesn't have support, and it gets abandoned, it can leave you in a very bad place. So you want to be careful about picking a technology or an approach. You want to, I'd say, bring a skeptical attitude to the table when somebody's telling you what to use. So instead, maybe a better way, instead of just looking at some huge list of what's out there, is to instead pick a general approach. People will often call this kind of a paradigm. It's an overused buzzword, but maybe it's fitting here, is to pick a general paradigm as the way you're going to do parallel programming, because as we're about to see, most of these approaches do fit themselves into some categories here. And let's step through them. The first one we actually know, which is message passing. And pretty much all message passing is done with MPI. It's been a long time since there was any competition to MPI to do this message passing kind of thing. As a matter of fact, MPI built on the only one that ever really had any serious popularity, which was PVM. A lot of the PVM people formed the MPI committee and continued on from there. It was a long time ago. So if you're going to do this whole notion of I want to move data back and forth, MPI is undoubtedly the most popular way to do it. It's been around, as I said, a long time now. It's very dominant in this space, and it's got lots and lots of tools and libraries and stuff to accompany it. So you know all the pros here. Now you're in a position to understand some of the cons that I glossed over. I first threw up this slide very quickly in our intro thing, but I glossed over the cons because you really weren't in a position to understand the implications there. Now you are. The cons of MPI are that we have to worry about low-level details like sending and passing individual messages and chunks of our data structures. And you might say, well, isn't that unavoidable? Well, we'll see some approaches. The next one, data parallel, where we don't have to worry about that low-level stuff. We do with MPI. And debugging, as you're no doubt right now in the process of finding out, can take some effort. You haven't seen a parallel debugger yet. We're going to look at that shortly. But it doesn't solve all of our problems either. But debugging requires you to think a little bit differently, because things can go wrong on different PEs. Instead of in one line of code, you don't have a bug on one line of code. You have one line of code that's running in 8 different places. That's more challenging. The domain decomposition and the memory management, the way we're breaking things up, we have to explicitly think about that, how we're breaking up our problem. And there are other approaches where that's not true. So people leaving this workshop that are going to off to develop new applications or port applications could face months of work to do a parallel port with MPI, depending on what you're doing and how complicated it is. So it's not one of those, let's throw some stuff at a program in an afternoon and have a parallel code. And there are other approaches where that is an expectation. So these are the cons, these are the drawbacks. Now but at the end of the day, you end up with a code that can scale to millions of cores. Let's see some of these other things that might be alternatives. Well, one that's been around for a long time and is well regarded in many ways is data parallel. As a matter of fact, data parallel has been around so long that it's now actually just a generic part of Fortran, for example, as a Fortran 90. So that gives you some idea. It's been 30 years now since Fortran 90 came out, and Fortran 90 has statements that are just data parallel. data parallel is a wonderfully simple and straightforward way of doing parallel computing because it just uses array statements. So in Fortran, you can have nice array statements like A equals 2, and it'll set a whole array equal to 2. And B, it can be set equal to some for loop in parallel like this to have some structure. And then we can do a statement like C equals A plus B, one line that adds these two arrays together. And so this all happens if it's run on a system with a parallel runtime in parallel, because this can be done one element of, so if we have a system with 16 processors, for example, instead of taking 16 cycles to do all these adds, processor 0 can say add 2 and 2 and get 4. Well, processor 15 is adding 8 and 2 and getting 10. So this is not only a nice, simple, elegant way to write array-oriented mathematical statements, it also turns into parallel code in a very straightforward way. So data parallel is wonderful, and it's built into Fortran 90. There are many aspects of this in things like NumPy with Python has borrowed a lot of this. The Julia programming language has built upon this. So there are lots of data parallel notation out there that you can leverage to do some very straightforward, simple parallel computing. And by the way, the communication, so that's the computation. How about communication? Communication, or shuffling data around, is also very simple array type oriented operation. So we can take an array B here and we can shift it, for example. So in this case, we're shifting the array B on the second axis, one slot. So it's going to shift this array here this way, and we end up with a new array here. So we can do second axis, actually it shifted this one up, I guess. So no, it shifted this one this way. At any rate, this is communications. It's just shifting array data around, and there's other ways we could permute the data as well. And it's parallel communications behind the scenes, because if this array is distributed and spread out amongst a bunch of different cores, it'll do behind the scenes, it'll move the data around. Actually, in many cases using MPI, somebody will write a compiler that turns this into MPI, and behind the scenes, it will take care of all the data movement for us. So wow, this is just so simple and straightforward. Why would anybody do anything else? Why are we screwing around with this MPI stuff when we can just do parallel computation and communication like this? And indeed, that's true. It's, wow, how easy to debug. It's line by lines of code. The compiler's done all the work behind the scenes. And indeed, if the world were made up of nice big square arrays, rectilinear arrays, it would be the ideal way to program. The problem is, and for our Laplace code that we're doing right now, our square metal plate Laplace code, this is undoubtedly the easiest way to do that code. To do a Laplace code like this is so simple to change from the parallel code into this. However, and this is not a minor however, the world is not made up of those shapes do not lend themselves to big square arrays as well. And whereas with MPI, we've seen we can adapt our code. Matter of fact, we spent this afternoon looking with advanced MPI at all the ways that help us to deal with irregular shapes. We see MPI has all these communicators to allow us to, I see my internet's unstable again, so I hope I'm not breaking up too much. With MPI, we have all the tools to transition from our square metal plate into the real world. With data parallel, you get stuck really hard, really fast. So the second that things aren't nice square arrays, these data parallel commands fail, and there's no plan B. People try to jury rig some statement. There really isn't a plan B. There's no way to make data parallel work well with irregular shapes and context. So if you're doing image processing, you got a bunch of pixels and square grids, that's great. If you're doing irregular meshes, not so great. And the real world problems turn out to get irregular mighty fast. So that's the reason data parallel hasn't taken over the world, is that it's incredibly friendly and great, and you should absolutely use it where you can. But when it starts to fail, it goes off a cliff mighty fast. There is no plan B for irregular shapes. Okay, how about threading, approaches to threading? This is something I haven't grouped together as threads, but I've already talked about OpenMP and how it's used for multi-core programming on a single node, a single processor even. And threading is where a thread is a reference to a single thread of execution that runs on a single core. And so this is the kind of thing that when you've got a multi-core processor, you want to become good at, take advantage of all those cores. And OpenMP is the most popular way of doing this. And so OpenMP allows us to do this with what are called directives. And these are basically just some hints to the compiler that say, hey, take this loop, the standard do loop in Fortran or the standard for loop in C, and just do it in parallel. Split these iterations up over a bunch of threads that will run on different cores concurrently. And it really can be as simple as this. We can end up with a nice speed up on this loop just by sticking in these directives. And that indeed is great. The only problem is that it's limited to that one processor, that one core, because it assumes all the data is just sitting around in some shared memory space. And any one of the cores can reach into any slice of A or B or C and work with it. And while that's true, that's great. But as soon as this data grows huge, like it does for a big distributed application running on 1,000 cores, then this technique doesn't work on anything that's not shared memory. So it's only good on a single node. There are multiple ways of doing threading. Threading, for example, in OpenACC is how we use GPUs. So if you do GPU computing, this is the best way to do it, is using OpenACC. It's a successor to OpenMP for GPUs, and it has the same directive-based approach. The directives are very similar. Here's a directive called kernels. It says turn this loop into a kernel that runs on the GPU. And then it goes and it takes this loop and runs it on the GPU. And you have something that speeds up, 5 times faster on this GPU card you plugged into your machine. And it's great. Now you can run your simulations. Instead of taking all day, they take an hour. So that's wonderful. And it's a couple directives and just a single loop. And that's all we worry about. We're not decomposing data. So these directive-based threading approaches are just great. There are some more primitive ways of doing threading. POSIX threads in the old days, or with GPUs. CUDA is still around because it was the early way of doing GPU programming. And so there's a tremendous amount of software written in CUDA, much uglier stuff to deal with, but it still accomplishes the same goal. It's threaded and allows you to speed things up. So these approaches with threads are wonderful in that we can apply them loop by loop. If we get an 80,000 line code and we just time it and find out that 60% of our time is spent in this one loop and 20% spent in this other loop, we can just go speed those 2 loops up. We don't care about anything else in our code. We never have to look at it. We can just throw some directives in at those 2 sections of our code, which might be a tiny fraction of the total code. Maybe it's 40 lines of code altogether. We stick in 4 or 5 directives, and now our 80,000 line code is running a whole lot faster. So, and that's not an unreasonable expectation. But we are limited to one node. That's all those techniques work on. They're shared memory. They only work with threads on a node. There are many, many implementations of threaded languages. There is the original old school way is pthreads, which then in the 90s turned into OpenMP, thankfully. With GPUs, there's CUDA and OpenCL, which these days OpenACC is the much more advanced way to do that. People are always coming up with new ways. Intel comes up with one every other week. And so they've had threaded building blocks and Silk and C++ over the years. And these days they have, they're really pushing their DPC++ compiler and SQL approach. We'll talk about that a little bit more in a second. But anyway, there are millions of approaches to doing threaded programming because it's pretty easy kind of thing. Compilers are pretty good at working at that level. So the pros are great in that it's easy to throw out your code and try it real quickly. The cons are that if you only do it loop by loop, that Amdahl's law thing will come back. So when I started talking about you speed up a loop to 60% of your code, well, now we're talking right away about Amdahl's law situations. We're willing to ignore 40% of the code. That's going to limit our scalability. We also can forget about going to multiple nodes. So that's a limitation of threaded approaches. Now, the data parallel approach is so attractive and so awesome and so friendly that people were unwilling to give it up easily. And so there is the idea, and it's not an idea, it's been around for a long time, and people have had compilers that do this effectively for a long time. There's the idea of taking and preserving the general idea of working with arrays and array notation, but adding in a little bit more flexibility so that you actually can, on a node by node basis, start to change the behavior a little bit and maybe deal with more regular data structures. And so these approaches are called PGAS, partition global address spaces. And they've been around a long time successfully. Co-array Fortran was around for a long time, so much so that Fortran has actually absorbed it into the standard. So regular Fortran, as of Fortran 2008, now has co-array Fortran statements built into it. So you can do parallel programming just with any generic Fortran 2008 compiler that supports it, which is, by the way, not most of the compilers. That gives you some idea about how sophisticated this stuff is that a compiler standard from 12 years ago at this point is still not caught up for most compilers with implementing this stuff because it is really tricky. But the idea here is, again, to have the friendliness of the data parallel approach, but have some flexibility to allow us to address real world cases that aren't just square arrays. And there's plenty of documentation and sources out there. So it's fantastic. You can use it. And it's wonderful, but it's been around a long enough time now, especially in the two popular versions of it, CodeRay Fortran, again, part of Fortran, regular Fortran these days, and the C version called Unified Parallel C, UPC. They've been around a long time now, and they really haven't gained a ton of traction. So although everybody's really hoping that people will figure out how to use this stuff well, you can't dispute that they just really haven't gained a lot of success stories. And I think at the end of the day, in my experience, by the time you get done tweaking all of these nice data parallel statements to make them more flexible and work with the regular data structures, you've essentially done all the work of an MPI domain decomposition. You put in all that level of effort. So you may as well just use MPI and have something that's more portable and generic and understandable. And so that's the reality. But the idea is so attractive that PDIS languages will continue to be supported enthusiastically and encouraged. One method that's overlooked a lot and I think underutilized tremendously is the notion of a framework where somebody else does most of the parallel programming and you just drop in your science. And this is something that I hope you can understand or getting some appreciation of as you just do the Laplace port. As you do the Laplace port, you're noticing that you're not changing the science part of the code much at all, if at all, right? The guts that actually do that Jacobi iteration, you're not having to touch very much. And B, you're using these communication halo routines that you're developing that I keep telling you are applicable to many, many other cases. So you get the notion that you're actually writing a generic communication scheme that could be used for lots of other problems, and you're not changing the science. Well, it's not a big leap from there to the notion that, hey, why don't we have some great MPI programmers, some computer science enthusiasts, write us that nice framework that does all the techniques I've talked about, like we talked about overlapping computation and communication and optimizing all the message passing, do all the really nifty, great stuff, do really good load balancing, and then let us just drop in our science. Let us just plug in that science part of the code and let it do all the other stuff. And indeed, that is a good idea at the point where Charm++ is a framework that has done that. It has done it very successfully with a very important application, NAMD. NAMD is a molecular dynamics package that's widely used. And NAMD is built in Charm++, and so it's a good example of how you can drop the science in and then use the framework. Now, as successful as this is, NAMD in particular, frameworks have also not gained a ton of traction. So this is one of those things that baffles me a little bit and is a little bit discouraging because I think these frameworks are underutilized, but I won't lie to you, that is the reality. And so Charm++ is just this wonderful example of it. It's, sitting there waiting for people to just stick their science in and take advantage of all the great MPI code that they've written. But nevertheless, it has a very limited sphere of influence, and that's after again 20 plus years. So be aware of it, but don't be aware of again its limited adoption. Now, as I was writing this slide a while ago, and I was thinking, yeah, it's still sad how frameworks are underutilized. I was also at the same time working on machine learning AI projects, which if you know anything about machine learning or AI, well, if you want to come to our big data workshop, but at any rate, the machine learning community has standardized around a couple of packages, frameworks that they use. Well, they don't call them frameworks. They, a couple packages, a couple APIs that they use to do most of their work. Things like TensorFlow or Torch. You may have heard of those just in passing if you heard anything about machine learning. And TensorFlow and Torch are very much frameworks. They are these great parallel libraries that you come along and using just a thin layer of Python on top of, you just glue together in ways to implement your science, your deep learning in most cases. And so they really are parallel frameworks that are widely used and very successfully adopted. So I think that is a plus for the framework approach, although most people really never think of it that way, but it absolutely is the case. So TensorFlow and PyTorch and some other ones that have come and gone like Caffe are very much parallel frameworks that people are using to do science. Although, again, even the scientists that use them don't think of that way. Now, there are, as I said, plenty of alternatives for all of this stuff here. We've got, I'll mention some of the ones that have come and gone or are still hanging around. You may have heard of OpenCL because for a while with it, so the original way of doing threaded programming on GPUs was CUDA, but it's very proprietary. It's NVIDIA, CUDA, it works on NVIDIA devices and only on NVIDIA devices. But NVIDIA has ruled the roost in GPU computing for a long time, to their credit, because they've given really good early support to GPU programming, and they did it with CUDA. So CUDA became kind of the standard, but it is tied to their hardware. And so an alternative was required for people that weren't willing to use it, commit to a proprietary API. And so OpenCL came along. The Kronos group formed to support it, and everybody supported it, including NVIDIA. To NVIDIA's credit, they supported OpenCL. And so OpenCL was a way to do threaded programming, particularly on GPUs, but really meant to support everything, including CPUs. And everybody supported it. But unfortunately, all of its primary supporters have now chosen other priorities. So Intel decided that they really cared more about OpenMP, although these days they got some other even things in the air. NVIDIA always had CUDA as a fallback. They didn't really care that much about it. And OpenACC has now succeeded CUDA and OpenCL as their preferred way of programming GPUs. AMD, who really benefited from OpenCL to support parallel programming on their devices because CUDA didn't work there, now has their own API for things. And so the Kronos group really doesn't have much industry backing, which is really important for something like this, because you need the engineers from the companies that build the hardware to be involved in the project. Yeah, the open source community can support, say, a compiler. Like the GNU compiler has a lot of just general open support from the community, and that's great because computer CPU architectures don't change a ton, from year to year. I mean, we make a big splash out of it when every year a new CPU model comes out, but they don't look drastically different than they did 10 years ago. Whereas GPUs have undergone incredible evolution, and they do change drastically. So if you don't have somebody from inside the company supporting stuff, it tends to fall behind. And OpenCL was always lagging in performance. Nowadays, it's just kind of moot. So I wouldn't recommend OpenCL to anybody to start a project with, certainly. And I hope you don't inherit something that's built around it, because it's now kind of deprecated. Even the Kronos group has now kind of succeeded it with SYCL. Fortran 2008 has threads built into it, along with, as I said, the PGAS version of data parallel stuff. But it's just the compilers do not consistently implement, haven't caught up with this. And again, the fact that it came out in 2008 is the standard and compilers are still struggling to catch up with it is a clue that it might have some portability issues. Let's see. C++ as of 11 standardized threads, which was nice, but they were kind of lame. They were very unsophisticated compared to other alternatives. They have gradually, as of C++ 17, that rolled in some better threads, and C++ 20, they keep improving things. So C++ keeps rolling in some better threaded models of programming, but they're still all lacking compared to OpenMP, which is also equally standardized and works on every C++ compiler. So I'm not sure why you'd ever choose any of them, but at least they're standard, which means they're safe to use if you want to. But until they catch up with the kind of nifty stuff like OpenMP can do, like tasks, I don't know why you'd make that choice, but it is there. So C++ continues to improve its threading. Python threads are fake. This is an unfortunate thing. That Python has a lock inside of it. If you were taking the OpenMP course, we could discuss this a little bit more meaningfully, but Python has a GILD, a global interpreter lock built into it, which makes it very, very serial. So Python just runs extremely serially. And so it has a thread library, but the thread library doesn't actually run concurrently. It just kind of runs sequentially. So there's no point in threading in Python. Microsoft always has some threaded library that they propose that you use, but it's not HPC oriented at all. So for science purposes, it's really not interesting. Although maybe if you're a video game programmer or something, the APA might be useful to you since it's coming along for the ride. C++, there are a number of very C++ oriented approaches. There's AMP for Microsoft, threaded building blocks, and Silk. So Intel's comes out with something constant. Like I said, Intel has threaded building blocks for a while. And if you still go to their pages on these things, they'll tell you, this is the way to do threaded programming. Use threaded building blocks. And you go to some other pages there. Use Silk. No, use Silk is how we should do threaded programming. And nowadays, the latest, greatest stuff is use the one API stuff, which is DPC++, which is an extension of SYCL. Use this to do threaded programming. So I would be very skeptical when Intel's telling you to invest in something, because they've already got multiple things they're telling you are the way to go. And so 5 years from now, who knows what's going to be abandoned and what's going to be supported. And none of them are compelling to me because they're still, in this case, kind of lame versions of OpenMP in most circumstances. The national labs, in an attempt to unify both OpenMP and OpenACC and multiple ways of programming GPUs and multi-threaded, have written a layer on top of that called COCOS. They've got a couple of them actually, but a lot of this stuff turns into what is a very good example of Lampson's law. So Lampson's law is Lampson's law is a pithy little statement saying all problems in computer science can be solved by another level of indirection, except the corollary for this is except the problem of too many layers of indirection. So in programming, there's always a temptation to say things are a little messy. I know, I'll slap another layer on top of it to clean it up, you know, and then eventually that layer, somebody decides that and adds another layer on top. But this is just a common theme in programming. I mean, it's, you know, you see it everywhere. You know, it's originally programs could be compiled with CMake. You know, well, anyway, I won't go through this, the long list of where we end up today because of too many layers of software making things complicated. If you work in any area of programming, you've stumbled across these things. I stumble across these all the time and everything where make files now are incredibly complicated, and Jupyter Notebook environments are incredibly flaky. Python environments are so tricky that a lot of people just give up and start bundling things into containers, and then containers get to be so tricky. So Lampson's law is everywhere in computer science. Parallel programming is not immune to it. And as a result, you know, here's where we are right now with parallel programming at the national labs, who are trying to unify things, in particular threaded approaches. One of the labs is a big champion of COCOS, another lab's a champion of Raja or the, you know, one API. Intel's really pushing, and you read their descriptions that are all overlapping and redundant and have a bunch of pieces and moving parts to make them work right. And so if you care about that kind of stuff or you're interested, I will encourage you to read this slide. Otherwise, don't, because it will just scare you silly as to how incredibly incoherent the modern vision of parallel programming is at the lab levels. And so this is why I feel very comfortable encouraging people to learn the standard, widely implemented techniques like MPI, because it will serve you well as the confusion reigns supreme in other areas of parallel computing. So I'll be glad to discuss any details of this with those of you that want to read through the slide or pick it apart or interested in this. Otherwise, I'll save it for the Q&A session. No, I don't want to step everybody through this. Instead, we'll get on to back to the topic of hybrid programming, which I mentioned briefly earlier in the advanced MPI talk. I mentioned that, you know, MPI works very well with all these other approaches because, well, they have to. If they want to be taken seriously, they have to work with MPI so that they can scale up on these big machines. And so it is not uncommon to find codes that have MPI and have on the to glue together a lot of nodes, and behind the scenes then on each node they'll use something like OpenACC to program the GPU or OpenMP to do multi-core. And so this is a common kind of design, and realize that if you're building a hybrid code, really think about the MPI layer first, because that domain decomposition is the most important thing. And then you can worry about addressing the hardware capabilities on individual nodes if you care about it. Otherwise, if you start out with what seems like the easy part to bite off, I'll do the easy stuff like OpenMP, which is indeed much easier. Adding MPI on top of that, now you've got multiple things to juggle. So you pretty much want to design an MPI code and then worry about making it hybrid. Although it turns out that a lot of times if you write an MPI code, you care a lot less about making it hybrid, making it multi-core than you might think. What do I mean by that? I mean, if you write an MPI code like on bridges, we're writing these MPI codes. We're running them right now on multiple cores on bridges. And if you keep scaling up, then you can grab multiple nodes on bridges, and you can scale up to use all the bridges, all the nodes and all the cores on bridges. And so you can see MPI is perfectly happy to work on a multi-core mode or work on multiple nodes across nodes. That's what MPI does. Then you might think, okay, so I never need to do OpenMP programming. I could just write MPI, so each rank, each PE is an individual core. And indeed, that's a way to go. Now, somebody else might say, well, yeah, but you know, OpenMP is especially designed to work on an individual shared memory node. So maybe you'll get better performance if you use OpenMP on the node and then you use MPI then to connect the nodes together. That's the most typical hybrid program that you'll find with MPI, is you've got MPI gluing a bunch of nodes together, and then on the node, you'll see OpenMP used to coordinate all the cores. And that's a very viable way to work. And again, MPI and OpenMP work very well together. So nothing wrong with doing a code that way. However, what surprises people is sometimes when they have a hybrid code like that, they'll turn off the OpenMP part and just run MPI to all of the cores. So you can just forget the hybrid part. We're just going to run MPI across all of the cores instead of using OpenMP on the node and using MPI across the nodes. And they find that the performance actually improves, but usually it's marginal. We're talking an effect of a couple percent here. But the very fact that the MPI to the core version runs faster than the hybrid version seems very odd, because isn't the hybrid version using the perfect tool for the job, the OpenMP on the node level and MPI across the nodes? And you put the extra effort in, so why isn't that the fastest version? And the answer is something that we can't dive too deeply into this workshop. In the OpenMP workshop, we can get more into it, because in the OpenMP workshop, we talk more about how cache and memory segmentation is an important part of modern computers. And on modern computers, because of the way they have caches and cache coherency and stuff going on, when you do an MPI domain decomposition and you break the data up into pieces, you can very often be doing something that's helpful to the local hardware, which is having each core access memory pretty independently and not get intertangled. That can buy you, without you even trying, that can buy you a nice cache coherency boost, which can be important. And so sometimes the MPI to the core, simplest way of programming, just use MPI to go to all the cores and forget the hybrid programming, can be faster than the fancier approach of using MPI between nodes and OpenMP on the node. And so it catches people by surprise, and yet it's a common enough thing, and it's not a mystery. But again, in most cases, we're talking a couple percent performance difference on the node. It's not a huge thing, but it is a common phenomenon. Okay, let me catch up on a couple of questions that I saw popping in here. Absorb poor scalability with TensorFlow. Well, that's a separate topic. In the big data workshop, we could talk about it. You can get excellent scalability with TensorFlow, and there are applications that run on tens of thousands of GPUs and scale very well with TensorFlow. So TensorFlow doesn't have an inherent scalability limitation built in, but you can do things that don't scale well as well. But again, we can't digress too far into that here. Let's see, Python's GIL is an implementation detail of CPython. Other Python implementation might be better. Well, in paper, yes. In paper, the GIL is an implementation of the one version of CPython. However, in reality, CPython is the only version of Python that anybody cares about, and all the libraries properly support. And so if you're using Python, at the end of the day, that's probably what you're using, unless you optimize and use something like CDEV Numba or something like that. That's a whole different story, a different level of parallelization. But in reality, we're stuck with CPython if you just want access to all the libraries and just want to import stuff by default, which is the #1 reason we all like to use Python, right? You can just grab scikit-learn to do some statistics here and grab matplotlib to do some graphs, right? And if you want to have all that at your fingertips, you're using CPython. So yes, in theory, the GIL isn't there, and people work on GIL-less versions of it and stackless Pythons and blah, blah, blah. In reality, none of those have the open portability and standardization. It's the whole reason that we use Python in the first place. But yes, that is true. Yes, if somebody actually made a generically useful version of Python without the GIL, it would be incredibly helpful to the whole world. It would improve performance on every Python application, or almost all of them that are out there that use CPython. Okay, so parallel programming in a nutshell here is we've got to break our problem up into a bunch of pieces. So all the different approaches we've talked about so far, they all have one thing in common, is that we've got to break something into pieces. Now with MPI, we break our data structure up into a bunch of pieces, and we work on our data as individual pieces and shuttle information back and forth. With some of the simpler things to use, like OpenMP and OpenACC, we break our loops up. If you notice, if you think back about what we actually did, we put those directives in front of loops, and the compiler automatically broke our loops up. So threaded programming, we break up the work. In MPI programming, we break up the data, and they're very different. And it seems like one is so much easier. We're just breaking up the loops, yes, but it's also limited to a single node, a single shared memory chunk of the machine. Breaking up the data, harder, takes more effort, but scales endlessly, as big a machine as we can get our hands on. The domain decomposition step, as I mentioned, is the most important thing. And we haven't gone into all the concerns you might run into, but I've mentioned, I think, the important ones offhand. Load balancing is certainly one. So with our weather map, for example, if we did a naive thing like break our weather map up into 50 states, which, to be fair, I suggested early on might be a simple thing to do, we would find ourselves with a real problem here, because the state that's responsible for Texas, for example, the PE responsible for Texas has a lot more work to do than the PE responsible for New Jersey. So when our weather model runs, this one's done real soon and is twiddling its thumbs, and everybody's sitting around and waiting for Texas to finish up. And so this is going to waste a lot of computing power. So we want to load balance. And you can imagine with the weather map, you go, okay, the obvious thing to do is just break it up by geographical area. We want roughly 50 equal areas. So that's how we'll divide it up. And okay, that sounds good. But how about when the weather's actually running and we've got, say, a hurricane coming up the coast? If you think about it, if you make a mesh, if you did any kind of reasonable meshing to capture the mechanics of a hurricane coming up the coast, you got a lot more activity going on where the hurricane is than maybe the middle of the country here where nothing's going on, the weather's very boring, and you don't need a lot of processing power. And so what we actually have here then would be a case where not only do we have a complicated mesh, but it's dynamic mesh. It's changing as the program runs. As the hurricane goes up the coast, the mesh should adapt with it. And this kind of adaptive meshing is an important thing to do for a large class of problems. But once again, MPI comes to the rescue because MPI is perfectly happy to give you the tools to implement adaptive meshing. Adaptive meshing, even more work and bookkeeping for you to keep track of. MPI tries to help you, but adaptive meshing is perfectly within the capabilities of MPI. This is where, like I said, data parallel, like you're completely lost. You're like, I can't deal with the regular meshes to begin with, let alone adaptive meshing. But with MPI, we can deal with the most complicated cases where we have crazy unbalanced meshes that are even changing as the problem runs. And so MPI has all of that power to it. But once again, to summarize here how the pieces fit together, right? I've shown you this slide a bunch of times, but if you walk away knowing this, you won't be confused. Again, we live in the age of multi-core computers, and OpenMP would work great to let you get all the power out of a single processor or a single workstation. You buy a GPU and plug it in. You could do something like OpenACC or CUDA, but if you want to scale beyond that, you need MPI, and you now know MPI. So where do you fit in the roadmap of the future? Well, lucky for you, if you know, now that you know MPI, you have a pretty good position, because if you look at most of the roadmaps written for large computing platforms, the exascale machines I've talked about, anything else that anybody's developing, these roadmaps have a term in it they call MPI plus X. So if you look through just Google web pages or look through project plans, you'll see people referring to MPI plus X. That's their way of acknowledging that the programming model for the foreseeable future on all these machines is MPI, and they usually mean like 3.0 or whatever, but that's not important. As we said, version numbers in MPI aren't that significant. They mean MPI, and the X means one of these heterogeneous things that we've been taught. Heterogeneous meaning helping the weird pieces of hardware we now plug in, accelerators and multi-core CPUs and all of those things, work effectively as well. So we know we need MPI across the machine, and then we need X on the local node to get all the squeeze all the performance out of the local node. And so the future for everybody is MPI plus X. That's a standard term you'll see everywhere. And lucky for you, you know the biggest part of that, MPI. And the X's and whatnot, you can are easier to learn. That's why our OpenMP workshop's only a day, and our OpenACC workshop's only a day. That in some sense is suggestive of the fact that they are simpler, easier technologies. So if you master MPI, you know the hard part of the puzzle for the future. And the X is something that's still uncertain, but they're easier and mutating pieces. So that's the top of anybody's roadmap. Now you'll also see on a lot of these roadmaps, people will say, yeah, but everybody knows MPI is hard to do. So we want one of these PGAS things that we've been talking about, you know, with PGAS, with Fortran, Code, Fortran, and whatnot. We want these PGAS things to work. So people have PGAS on their roadmap too. But again, PGAS languages are not new, even though people might imply it. They've been around for a long time. Again, Fortran 2008 has it built into the standard. That gives you some idea that it's, and obviously to get into the standard, it had to be pretty conservative and established before that. So it goes well back into the 90s. And yet, you know, PGAS is still not caught on completely. So PGAS is the next thing in the ladder, but it's a big step down. And then behind that, you have even fancier approaches, like you have these synchronous PGAS languages, which are these days, actually, these are also quite old. I was about to say newer, but X10 and Chappelle have been around for 15 years now, something like that. These have been around a long time too. They're fancier versions of this. They have yet also to catch on and really establish a lot of traction. You have the frameworks we've talked about. There's always somebody coming up with something new. There's always somebody that's never done any parallel programming that suggests that if you just pick the right programming language, this is all easy and take care of itself. You know, usually it's a Haskell fanatic or something like that. And indeed, there are programming languages that have parallelism built into them in a more natural and elegant way, but they also typically, for example, don't deal with, you know, internode communication. So there's always somebody saying, yeah, if you just choose the right programming language, this is great. But ask them, say, okay, what applications are using your approach and how do they scale? That scalability question is always a reality check. You ask somebody, how does your application, your programming language, your hardware, how does it scale? If they don't have a scalability graph to show you, right away you can dismiss them as somebody that's more dreams than they are reality. So those scalability graphs are very much reality check. If somebody tells me about their latest, you know, parallel programming approach, I say, oh, how's it scale? And if they're serious, they pull out their scalability graph and they brag about it. Look at how we're scaling great. We're at 2,000 nodes and still scaling well, and blah, blah, blah. And we're going to push it even more. We know what the bottlenecks are. But if somebody says, oh, we haven't done the scalability studies yet or whatever, then like I said, you might want to reserve your enthusiasm a bit. Okay, well, do you really care about all the other software pieces floating around out there too? You know, and the answer is, of course you should. And just to quickly give you a very light survey, I'm not going to go through all of these slides here, but you can if you care about it. Here are, from the Exascale computing project, here are the different application domains of applications that they intend to have coming up on day one when these machines come up very shortly. So these are applications that have already been developed for this stuff and ported or porting to this environment. So these are not just long-term plans. And you can see they span a lot of different areas, very diverse applications. And here is a little bit of their software kit, basically, that they're guaranteed support for day one on these platforms. And a lot of these pieces here, or most of these pieces, are straight up MPI packages that are just meant to work with MPI, things very popular like PET-C, Trilinos, SuperLU. These are linear algebra and math packages and solver packages, and they're all implemented in MPI and, you know, meant to interoperate with MPI. Here's the software stacks that they're talking about on these machines, and you can see, well, you can't because you're not familiar with the software environment yet, but an awful lot of these pieces are just, hey, things that are meant to work directly with MPI or help out MPI, whether they're performance profiling tools like Power Pappy, or whether they're libraries over here. A whole lot of this is just simply, hey, here's how to make MPI programs work more effectively in this environment. That should make you confident. And if you want to see examples of the kind of applications that these things are targeted to, here are a bunch of them, and these are all MPI-based things. And I won't step through these, but I just give them as a teaser to you. They're not by any means comprehensive, but these are applications that are very much meant to day one be working on these Exascale platforms, and they're all running on the pre-Exascale platforms. So if any of these strike your attention in particular, let me know. We can talk about them a little bit because I'm familiar with many of them, but that's just a sampling of those.